So features orthogonality. That's mean the concept behind these features in technique is that the more different features that we are taken, the model will be more better. So the main concept behind it is the more different the features are, the better model. A better model you will get. That's the main key concept behind this features engineering. So in different, in another language, this you can think like that. Different in mathematically, it's called the orthogonality. Orthogonal or different in mathematically, it's called orthogonal. In English language, it's called the different. So suppose let's take we have three features. Suppose we have three features f1, f2, and f3. These three features have. And onto these three features, we have built some model. We have interest to build some model that predict some output, that will give some output. Okay. Now the questions is if we have here somehow three features. Let's take let three features. If the features one, suppose the features one is correlated to this features y. Suppose let the features one, using some domain knowledge, some external knowledge, we have known the features one is correlated to the output of this model. It's correlated. Similarly, F2 is as well correlated to the output of that model. Correlated. Similarly, F3 is also correlated to the output of this model. Okay, using some domain knowledge, we got this thing. Okay, if this happen, then suppose let if this thing happen, then and from these features also we know the F1 is also correlated to F2 and F1 is also correlated to the features F3 and features F2 is correlated to F3. Means the H1 is correlated to others. H features is correlated to others. If this thing happens, in such scenario, the model means just see it. Here, H features are correlated to our models and H features is also correlated to the other features. Because of these reasons, the model that we are want to build, it's not so much effective. Because of these reasons, here model is not so much effective. Because of these reasons, since each features is correlated to each other. Now let's try to understand through this different example. Now let there have three features. We have three features f1, f2, f3, and from these features we are interested to build a model that will predict our output. Okay, and let f1 features is correlated to the y F2 features is correlated to the, and similarly F3 is also correlated to the output of that model. Correlated. But here is make difference is each features is not correlated to each other. Okay. Suppose the features 1, here it is not correlated. F2, and similarly F1 is not correlated to F3. And since F1 is not correlated to F2 and F1 is not correlated to F3, that means, and let also F3 is not also correlated to F2 is not also correlated to F3. If this thing happens, then we can conclude that since the output of that model is correlated to edge features, but edge features is not correlated to each other, then we can conclude that this model is so much effective because of its independency. We conclude that the model M would be effective because of its independency. Because of its independency, this model M must be effective since the edge features is not dependent, but it's dependent on, but it's correlated with the output, but it's not correlated with the each other. Okay. So since because of its independency, its model will be more effective. So now let's our task is we have to build another features that we are interested to build another features F4 that we are interested to build. We have interest to build F4, and this F4 must not be correlated to the other features. How we'll build this thing? Let's see. Now let's see things. The F4, it must be correlated to the output of the model. It must be correlated to the output model, but F4 is not correlated with the other features. The other features means F1, F2, and F3. Okay, how we'll doing this? Okay, how we'll do it? I mean, idea of it. The idea of it is, so by simple using the error concept. So the data set that we have. Now let's try to understand that. So the data set that we have here, F1 features, F2 features, F3 features, and also there have corresponding Y and YI hat. Means this Y is the actual output and this Y is the predicted output. These things are called the actual output. And this YI hat is called the predicted output. Okay. Since already we have got this to output, already we have known this to output. Means from these features, three features, we have already built our model. Okay, we have already built, and since we have built the model M, then based on the output of this model, we can predict the corresponding predicted output, each data points. So suppose let's say here we have the xi's. Okay, so now based on this, how to build the another feature? So F4 that will be not correlated to these features. How will doing this thing? So the questions, it will better if we write the question first. The questions that come into our mind: how do I design a new features F4 such that F4 is correlated with Y, but it is less correlated with the other features F1, F2, 3. Now let's see it. How we'll solve this thing. How we'll solve this. See it. What will be its solutions? So since we have known its output, original output and predicted output, we can easily calculate its error. So for all the data points, xi's, we can easily calculate its error or error I. So it will be yi minus yi hat. Okay, we can easily calculate these things, and these things are called the error. These things are called the error. Okay. Now the features that we are want to build F4. Now the features that are want to build F, it must be correlated. If somehow we build it, must be correlated to this error I. To this error I. This error and this error are the same. Then we can conclude that. F1, F2, F3 are less correlated by the features F4. Since just say it. By using these three features, we build the model, and based on this model, we got the output yi hat. And the error is the differences of the original output and the predicted output. Since this error is correlated to this F4, so this F4 must be less impacted. Is F1, F2, and F3. Since F1, F2 are related to the F1, F2, and F3 are related to the yi hat, and yi hat and difference between actual to minus predicted is ei. Since because of these reasons, F4 is less correlated with these three. That's the simple. Okay. That's the simple idea behind. Okay. So the thing, the same thing also you have seen in the GBDT. If you remember the GBDT technique, and the same concepts we have. In GBDT, we have using the GBDT, we have built some model. Suppose let model 1 we build onto it, and on this model we make got the error, we find the error, and based on this error we build another model. So this model, this error based on this error that we got from this model 1, this error is less impacted by this model 2, on model 2, less impacted on model. So this error is sometimes called the pseudo error. This error is sometimes called the pseudo error. Okay. And the idea behind is that you can boosting technique, various kind of boosting technique. It's one of the example gradient boosting technique. If you apply the boosting, various kind of boosting technique, it's one of the idea is Gradient boosting. Gradient boosting. That's the simple same things also we have. Okay. So I think from this idea you got the concept how these things are actually useful to build a new features that will be more different the others. But as always, there have some problem. This method. There have some drawback. As always, they have some drawback on it. Drawback is like that. So drawback is the features. F4. It's correlated to the error. It's correlated to the error EI. This is the actual error correlated to the error. And the main problem is the overfitting. Overfit. The main drawback is the overfit. Main drawback here is the overfitting problem. That's the main drawback. So now, how to avoid this drawback? How to avoid this kind of drawback? How to avoid this kind of overfitting problem? How will remove these things? Okay, by simple using the concept the hyperparameter. So we have used here the hyperparameter. Using the hyperparameter to avoid this overfitting problem. So we will see, we will just in discussion, we will see the features F4. The features F4 is correlated to the error, means the yi minus yi hat. That's the actual error. These features are correlated with this error, and using this simple technique, and these features which are less correlated with the other features. These features are less correlated with the other features, means F1, F2. We have seen it. We have seen this thing. Okay. The simple concept is the features orthogonality, means the more different features we will select, the more better model we will got. That's the main concept behind it. Okay. And to build a new features that are less correlated with the other features, we will simple using this simple technique. Once the error that we will got, the features we want to build and the error that we will got, that must be correlated. Using this simple technique, we can build such kind of features that will be less correlated to the other. This is the simple thing. We'll see when we discuss the case study. We will see in its applications in